This is the solution to question 3 on page 500 in Text and Tests 4, and it is a proof by induction question. So this question is a series type question for proof by induction, and it's asking us to prove that 1 by 2 plus 2 by 3 plus so on and so on up to n times n plus 1 equals to n over 3 times n plus 1 times n plus 2. And the first thing to notice is that I've just left a little bit of the statement out from how they presented this in the question, which is the series presented in summation form. And just to point out what this actually means, it's just basically an abbreviated version of this left-hand side of the equation here. And I'm starting at n being 1 and I'm going up as far as n. And so you can see there, if I was to substitute in here for the first term, where n is 1, I'd have 1 by 1 plus 1, that's 1 by 2, that's that term. Then the next term is n equals 2, so I'd have 2 by 2 plus 1, that's 2 by 3, that's that term, and so on and so on and so on, up until I get to n, in which case I've just got n by n plus 1. You'll see there when we have our series notation written this way, that it actually tends to link in to the last term on that left-hand side. So now I want to go through my steps for proof by induction, the first step being to prove that this is true for n equals 1. So I take my proposition and I substitute 1 into it and I see what the result is. Now for the case of n equals 1, I don't need to have a whole big long chain of information here on the left-hand side. The 1 here indicates that I'm looking at the first term. So it's just 1 by 1 plus 1, which is 1 by 2, which is just this first set of values here. And on the right-hand side, then I'm just substituting 1 in for n. And then I'll go ahead to evaluate both sides, and I'll get the really obviously true statement that 2 equals to 2. So I'm just going to state the obvious there that P1 is true. You can also say that the statement is true for n equals 1 if you prefer to phrase it that way. My next step is to assume that pk is true. Now for this line, I'm essentially going to rewrite the original line of the question, just substituting k in for n. So this looks pretty much identical to my initial line up here, but like I said, k's instead of n's. I don't need to do anything else with this just yet. I'm really going to use this when I get into step 3. And step 3 requires me to investigate the proposition with k plus 1 substituted in as a value, and I want to then try and prove that that resulting algebraic statement is true, and I'll be incorporating step 2 to do that. So when I was doing pk, I went this far because I got to the kth term or the nth term. And so in this scenario where I'm doing pk plus 1, I want to go to the next term on, so not just to the kth term, but to the k plus 1th term. So to achieve that, what I'm doing is I'm at the very end of my series, I'm putting k plus 1 in for n. So I've got k plus 1, and then k plus 1 plus 1. That's that extra plus 1 from up there. And on the right-hand side, I'm substituting in k plus 1 for n. And now what I need to do is just resolve both sides. And, well, actually, sorry, before I resolve both sides, I need to get this more manageable over here, don't I? Because dot, dot, dot isn't any good to me. And what I can do at this stage is I can look back to my second step and say, okay, well, I made this assumption that all of this stuff here equals to k over 3 times k plus 1 times k plus 2. And if I look closely at step 3, I can see that that information from step 2 is being repeated. So instead of writing it like this, I'm going to use the right-hand side of step 2 and substitute it in. So I'm starting by writing that down to replace this information here underlined in orange. And of course, I mustn't forget that I don't just finish there. I've got this extra stuff here, k plus 1 by k plus 1 plus 1, which is just k plus 2. And I'm writing that down here at the end as well. And I also have to include my right-hand side of my equation. And I'm just tidying up a little bit there in the process as I go along. Okay, now at this stage, then I want to resolve both sides so that they look the exact same. And then if I can get them the same, I can say that the statement is true. So first of all, I'm multiplying out these brackets. Now I've taken a little bit of a shortcut to end up at k squared plus 3k plus 2. Feel free to do it in a couple of lines if you need to. And then I'm multiplying out these brackets here also. And they give me k squared plus 3k plus 2. And then on the right-hand side, I also have to multiply. And over there, I get k squared plus 5k plus 6. I'm not really loving that I've got the over 3's. So what I'm going to do is I'm going to multiply across this entire equation by 3 just to make things a little bit more user-friendly, as it were. And just watch out there, when I'm multiplying this first term by 3, I'll just multiply once, and I can actually effectively cross off this 3 here in the denominator as a result. And I must multiply all of this stuff by 3 here. So I've done that to each individual term. Notice I'm doing it to each individual term here because this isn't in a bracket, whereas this was. I had something multiplying by something already. So when I multiplied in by 3, I only had to multiply it in by one of the things that was multiplying. And it's a similar scenario on the right-hand side. I've got k plus 1 over 3 multiplying by this bracket here. I'll only multiply this whole chunk of information once by 3, and effectively that means cancelling off the 3 on the bottom. And then I just have to multiply it on both sides and check what I get. And then tidying up my like terms on both sides, I can quite clearly see I'm getting the exact same thing on both sides of my equation. That's exactly what I wanted to happen. Now, because my equation equals on both sides, my equation is true, and that means that I've proved the proposition using k plus 1 is true also. Again, I'm going to state that. And then I'm just going to wrap up my concluding statements. So I can say, but p1 is true. And then we can say, well, it must mean so that it's true for n equals 1, n equals 2, and all values of n is an element of n, since we've just discovered that pk plus 1 is also true.